Welcome. In today's lecture, which is number 33, I want to catch you up on what's been happening in astronomy since we last discussed it. It's funny how often in science we tend to move from the realm of the very small, like the consideration of atoms and molecules we examined in the last lecture, to the very large, the world of astronomy. But that move, which involves the question of how the microcosm and macrocosm resemble each other, seems to happen a lot. It certainly was a theme that occupied natural philosophers in the early modern period, and it continues to be something we find even in the latest theoretical physics of our own day. The more we investigate the origins of our universe, for example, the more we realize that the realm of quarks and the like is extremely relevant to finding out how the Big Bang proceeded, how, that is, the universe writ large unfolded. So you won't be surprised to learn that at the very time when Berthollet and Proust were arguing over whether proportions of chemical reagents were fixed or infinitely variable, that's the question with which we began the last lecture. At this same time, a grand hypothesis about how the solar system originated began to claim attention. It came to be known as the nebular hypothesis. And while it had more than one originator, the most famous version belonged to our old friend Pierre-Simon Laplace, the French Newtonian astronomer and mathematician. Now, before I describe this theory to you, let me tell you a bit about nebulae. Nebulae are fuzzy objects in the heavens that had been cataloged by astronomers since antiquity. That is, the naked eye observations of the ancient astronomers had noticed that some objects in the heavens were unlike others in that they were less sharply defined. They weren't like stars. They were fuzzy, nebulous. Over the years, the number of such nebulae had increased because when the telescope was invented and turned onto the heavens, more were found. Sometimes the magnifying power of the telescope suggested that fuzziness in the heavens could be resolved into stars. Galileo, for example, was convinced that nebulous stars were actually a number of small stars clustered together. In his famous book of 1610, The Starry Messenger, he even sketched out the pattern of stars responsible for a couple of nebulae known at the time. His telescope had made it possible for him to see the stars, where observing with the naked eye revealed just a fuzzy patch. But even though the telescope increased the number of nebulae, it didn't always help to make them less fuzzy or to resolve them into individual stars. In the 18th century, the number of nebulae increased again due to the powerful new telescopes that William Herschel and his sister Caroline had when they undertook a systematic sweep of the heavens in the 1770s and 1780s. And that resulted in more nebulae being uncovered. Caroline herself discovered 3 new ones. Well, of course, this was right around the time when Laplace was coming into public notice. After the Revolution, when things had begun to settle down a little, Laplace published his System of the World. That was in 1796. I talked briefly about it back in Lecture 2. There we were concerned with the work because it portrayed a cosmos that could run by itself without needing to depend on God's direct action. And in the last lecture, we heard Laplace musing about a mind which, if it knew all the forces of nature and the respective positions of matter, a mind that would know everything about nature, past, present, future, with certainty. Laplace was, you'll recall, a deist par excellence. He believed God created laws of nature that were, by themselves, able to accomplish what God intended for the physical world. This way, God didn't have to constantly interfere. So Laplace tried to imagine how natural laws, all by themselves, might have produced the solar system we know from a primitive state. This was his famous nebular hypothesis. He postulated that there had originally been nothing more than a rotating, primitive, nebulous solar fluid. Then gradually, as the result of gravitational force, the fluid began to contract, and as it did so, it rotated faster and began to flatten. What eventually resulted was a central mass surrounded by smaller masses that revolved around it, all spinning in the same direction and roughly in the same plane. The central mass became the sun, and the smaller revolving masses cooled into the planets. Well, Laplace's nebular hypothesis was extremely attractive to anyone disposed toward deism. And, as I'm sure you'll agree from what we've learned in these lectures, there were such individuals among the natural philosophers concerned with both physical and biological realms. Laplace's nebular hypothesis exhibited more vividly than many other examples of deistic natural philosophy how natural law could take the place of God's direct action. Perhaps you'll remember that the nebular hypothesis was the basic inspiration for Chambers' slogan, "Creation by Natural Law," in his bestseller on the vestiges of the natural history of creation. The laws of matter by themselves produced a solar system from a primitive, homogeneous, nebulous fluid. Well, between 1799 and 1825, Laplace went on to establish himself as the Newton of the 19th century. We saw in Lecture 2 how he used Newton's laws to demonstrate the stability of the solar system, but he went on to develop other aspects of Newtonian analysis as he perfected celestial mechanics, even creating new mathematical techniques in the process. More and more of his analysis came out. He'd undertaken a grand project he called simply Celestial Mechanics, and every so often a new volume of it would appear. Eventually there were 5 volumes to the set, making him the world's authority on the movement of the heavens. And all this was not to be lost on the English. That was due mainly to the work of a remarkable woman named Mary Somerville. It was Somerville who provided English readers with a translation and commentary of Laplace's work in 1831. She'd been born Mary Fairfax, the daughter of a Scottish naval officer. Her mother taught her to read the Bible, but other than that, her parents didn't provide for any other childhood education. By the age of 10, she did briefly attend a boarding school, and later she took lessons in music, arithmetic, and painting. All this was fine, but it doesn't at all explain how Mary Somerville could have accomplished what she did later. That's much better understood when you realize that early on she began taking responsibility for her own education. First, she educated herself in languages. That, as we'll see, would later prove to be very important. Then she came across Euclid and found herself intrigued. Her parents didn't encourage her interest. On the contrary, they worried about the effect all the time she was spending on mathematics might have on her development into a proper young lady. When she was around 15, she came across algebra, of all places in a magazine for ladies. Needless to say, Mary persisted in her desire to learn more about mathematics. She did the best she could on her own. Eventually, at the age of 24, she married a man who, like her father, was a naval officer. He had no real patience for his wife's curious interests, provided no encouragement to her. But her husband died after only 3 years of marriage in 1807, leaving her alone in London, where they had moved, with 2 small sons. So Mary decided to move back to Scotland, where she would have the supportive family. But she also soon discovered other benefits to her move back to Scotland. I mean by that the encouragement she got from some of her acquaintances to persist in her study of natural philosophy and mathematics. John Playfair, for example, the popularizer of Hutton's theory of the earth, not only encouraged her, but put her in contact with a professor of mathematics at a military college. So her life had taken a positive turn in spite of the loss of her husband. Then in 1812, fortune smiled again, this time in the form of marriage to a man who was extremely supportive of Mary's intellectual interests. And he was well connected. This was William Somerville, a hospital inspector. In 1816, the couple moved to London, where William had been appointed inspector to the Army Medical Board. This extended the circle of her contacts to include many of the English natural philosophers. One in particular, the budding young astronomer John Herschel, son of William Herschel, who had by then moved to Britain, would remain a lifelong friend. In the course of 3 European tours, Mary continued to meet and exchange views with leading lights of French natural philosophy. Among the many she met, for example, was Pierre Laplace. So Mary Somerville became a known figure among the natural philosophers of the 1820s. She published her first paper on magnetism and colored light in the Transactions of the Royal Society in 1826. It made perfect sense then when the members of the Society for the Diffusion of Useful Knowledge were looking for someone who could translate Laplace's multi-volumed celestial mechanics into English that they approached Somerville. The challenge was formidable. How could she be loyal to what Laplace had technically achieved and still communicate to the average educated English reader? What she ended up doing was to provide more than a translation. It was a translation with commentary. She completed the task in 1831 in a 4-volume work, which included a preliminary dissertation that located Laplace's achievement within the history of Newtonian astronomy. Her accomplishment was universally praised for making Laplace accessible, and it certainly established Somerville's authority as a scientific figure in Victorian Britain. When you look at her work, in particular her commentary and the preliminary discourse, you catch a glimpse of Somerville's understanding of the meaning of physical science. Laplace's achievement was the occasion for her to celebrate natural science as a support for basic Victorian values. Somerville's understanding of the cosmos Laplace had mathematically described indicated clearly that it hadn't happened by accident. It must have been designed. She saw science as an ennobling activity that also promoted humility. Yes, the world was stable and enduring, as Laplace had shown, and science was a heroic and progressive social enterprise. This was precisely the kind of exposure that helped bring attention to natural science among the public, just as did the founding of the British Association in the same year Somerville's translation came out. So, Laplace's name was well known in Britain by the 1840s. Both his nebular hypothesis and his more technical astronomical analysis. As far as the nebular hypothesis was concerned, it was more controversial than anything in the technical volumes. I think you can see why. The nebular hypothesis was what we might call in-your-face deism. It forced the issue. It was saying that you didn't need God to explain how the solar system came to be. No more could you be content with the "in the beginning God created the heavens and earth." That wouldn't fly according to the great astronomer Laplace. In the beginning there was a slowly rotating solar nebulous fluid. So you can see why the nebular hypothesis enjoyed both supporters and detractors in the first half of the century. In Britain, 2 popular authors championed the nebular hypothesis. You'll recall that Laplace's scheme was given a central place in the Vestiges of the Natural History of Creation of 1844. For the content of the nebular theory, Chambers hadn't had to rely directly on Laplace himself. Just as Laplace's technical work was made available by Somerville, Laplace's nebular hypothesis had been explained to English readers by the British astronomer John Nicol, who had championed the theory in his popular astronomical writings. And Nicol was a friend of Chambers. When you looked into what Nicol had to say, you could see quickly where he stood. Nicol wanted you to believe that everybody who was anybody acknowledged the truth of the nebular hypothesis of the great Laplace. In fact, he maintained that the great truths in astronomy were being discussed in almost every popular periodical as if they had already become common knowledge. Well, that wasn't quite the way it was. The nebular theory was not, of course, without its detractors. Many people saw it as tantamount to atheism, since it replaced God as creator with natural law. Note again how hard it was for deists to avoid the charge of atheism. They claimed that they were enhancing the glory of God by showing how great God was when he imposed laws on nature. But this tactic never seemed to work. In the eyes of many, the remote God of deism was equivalent to no real God at all. So the nebular hypothesis had opponents because of the religious implications it appeared to carry. But there were also those who disagreed with the content of the theory itself. Some argued, for example, that the supposed primal fluid that made up nebulae was not really a fluid at all. Galileo had exposed his nebula to be individual stars once you had a telescope that could reveal them. Who's to say that Laplace's allegedly nebulous fluid wasn't really made up of stars too? Those who held this view of things found no comfort in the latest attempts to resolve nebulae into stars with the telescopes of the early 19th century. Nobody had been able to show that the large nebulae that were known were made up of stars. One of the nebulae that had attracted a lot of attention, for example, was the great nebula in the constellation Orion. It was massive, it was easily seen, and it had an irregular shape. And here came the rub. When you used even William Herschel's famous telescopes to look at it, you couldn't see any signs of resolvability. So the debates raged. Some argued that if we had more powerful telescopes, the nebula would be resolved into stars, thereby showing that there was no primal fluid of the kind Laplace had talked about in his nebular hypothesis. In 1826, John Herschel published an impressive engraving of a sketch of the nebula so everyone could see its irregular shape. Why did it have the shape it did? How did that fit with Laplace's idea that over time the primal fluid flattened out into a disk? Well, the issue became focused when the Earl of Rosse completed construction of a new telescope, the world's largest. It was a gigantic reflector nicknamed the Leviathan of Parsonstown, which was where it was located. In 1845, he turned it on Orion. There must have been some, those who were aware of the issue and aware of what the Earl was doing, who held their breath. What would the new telescope reveal? Would it resolve the nebula into stars, thereby discrediting the nebular hypothesis? Or would the nebula resist being resolved, giving comfort to those who believed in the existence of an irresolvable fluid, like the one Laplace had described? Well, the world was not long in waiting. Lord Rosse's Leviathan of Parsonstown did, in fact, resolve the grand nebula into stars. There was no fluid here, at any rate. Shouts of joy rang out from those who opposed the nebular hypothesis. I'm being a little dramatic, of course. And the Earl did more. He also was able to show for the first time that some nebulae had spiral arms, which he conjectured to be rotating masses of stars. The opponents of the nebular hypothesis regarded Lord Rosse's resolution of the nebula into stars as wonderful news. And they weren't only conservative religious minds either. The author of the famous Confessions of an Opium Eater, Thomas de Quincey, happily regarded Lord Rosse's result as the death knell of the nebular hypothesis. For de Quincey, the issue of the nebular hypothesis raised the specter of humankind adrift in the cosmos. Laplace's scenario of creation meant to him that there'd been no point to creation. It was an early version of the existentialist theme we would hear later at the end of the century. How could we be going anywhere if we were just the byproduct of natural law? But all these shouts of joy fell on deaf ears where the defenders of the nebular hypothesis were concerned. To them, Lord Rosse's resolution of the Orion Nebula did not destroy the nebular hypothesis. Men like John Nicol and Robert Chambers simply argued that nebulae came in two varieties, those that could be resolved and those that were genuinely nebular fluid. So as a result, the nebular hypothesis continued to be debated throughout the century. And incidentally, this idea of development in the physical world as the result of natural law, the debates over that notion continued to prepare the way for acceptance of biological evolution, just as they had been doing ever since the Vestiges first popularized the issue in the mid-1840s. And as we've already seen in recent lectures, both the nebular hypothesis and biological evolution would clash with the new ideas of thermodynamics, making the 19th century a fertile era for scientific controversy. Well, there was another major discovery in astronomy around the same time as Lord Rosse's development of his telescope. This one involved a new planet. The ancients had named 5 planets, other than the moon and the sun, which they also regarded as planets. For the ancients, there were Mercury, Venus, Mars, Jupiter, and Saturn. That arrangement changed once the Copernican system became established, because then the Earth became a planet, so there were 6. The only addition to the planets since then had come in the late 18th century. That was when William Herschel discovered the planet Uranus. I've mentioned William several times now. He and Caroline's telescopes were the best in Europe at the time. The brother and sister team had developed careful and painstaking techniques of polishing mirrors, and their efforts paid off. But discovering a new planet also took careful observation. In 1781, William noticed an object that he first took to be a comet. It wasn't an unknown object. It had been cataloged before, but nobody had detected its motion. So when William noticed that it had motion, he assumed he'd uncovered a new comet. Eventually, Herschel realized that this was no comet. It was a new planet circling the sun. So Herschel named it Uranus for the Greek god of the heavens. Once other astronomers learned about the new planet, they set out to determine the precise nature of its orbit. It was way out there, well beyond Saturn, so it would take a long, long time to go all the way around the sun, over 80 years. After several years, the astronomers were reasonably sure they'd established the orbit of the new planet, even though they'd only been able to observe just a portion of it. Well, the novelty of Uranus began to wane, as you can imagine it would. After a while, it wasn't observed that much anymore. During Napoleon's reign, for example, only 2 observations a year were made of it. But then in 1820, some additional old observations of Uranus were uncovered from before the time it was recognized as a planet. These were observations that had been made of what was thought to be a star. So astronomers checked them against where their established orbit for the planet would have put Uranus back then, and they found discrepancies. How to explain them? Well, one way would be to suspect the old data. Maybe these older observations just weren't that accurate. Some, in fact, did argue that this was the case. But it soon became clear that wasn't enough to take care of the problem. Something strange, indeed, was going on with Uranus's orbit. As time passed, various hypotheses were offered to account for it. On into the 1830s, some said that maybe Uranus had a massive satellite that was perturbing its orbit. Others that it had been struck by a comet. Some even wondered whether gravity's law changed at great distances. But the idea that held most merit among astronomers was that an unknown planet beyond the orbit of Uranus was causing it to deviate from the path that had been established. And in fact, this errant motion of Uranus as it circled the sun would be the occasion for uncovering yet another new planet. But the discovery of the new planet turned out to be a story of frustration. And it also would be a story that illustrates how national rivalries can affect the development of natural science. So let me tell you the story. There was a young Frenchman named Urbain Le Verrier, who was particularly suited to the challenge this problem represented because he specialized in the mathematics of Newtonian celestial mechanics. So he took up the problem in the 1840s. At the same time, over in England, a man named John Couch Adams, who was also a gifted mathematician, was working on it as well. The assumption was, again, that an 8th planet, farther out than Uranus, would occasionally move close enough to Uranus that its gravitational pull would cause Uranus to move out of its predicted orbit. So the problem was, how big would this planet have to be, and where would it have to be to exert the kind of tug that would pull Uranus into the path it was now seen to be moving? That's not a trivial mathematical problem, as you can appreciate. By the fall of 1843, Adams had a preliminary solution, but he needed the latest data on Uranus's position before he was willing to make his final determination. Well, he got the information he needed from astronomer colleagues, but the problem proved more difficult than he imagined. Where I live in Florida, we have a long, straight stretch of one of the well-traveled streets in town where our local astronomy club has laid out the solar system alongside the road. The planets are all depicted by impressive towers spaced proportionally from the sun. So as you drive by, you see Mercury, Venus, Earth, and Mars all pretty much bunched up around the sun. Then things start getting farther apart. The greatest distance of all is that between Uranus and Neptune. It's an incredible stretch. So Neptune is way out there. As Adams tried to be precise about where exactly the planet would have to be, it wasn't until the fall of 1845 that he'd worked out his final solution as to where he thought the new planet would have to be if it was to have the effect on Uranus that everybody was observing. Once he had it, once he figured out the location where the new planet would have to be, he sent it to 2 British astronomers and asked them to look for the new planet where his solution indicated. And now we begin to encounter a tale of frustration. When they got Adams's solution, the astronomers didn't just stop what they were doing and look for the new planet. You might think they should have, but they didn't. It was for a variety of reasons. They had their own work to do. This wasn't a high priority for them, and telescope time was, after all, precious. For another thing, the weather had to cooperate, and in England that's saying something, as you know. Besides, some used the excuse that they didn't like Adams's method for solving the problem. Meanwhile, over in France, Leverrier had also been working out a solution. He submitted a preliminary paper on the problem in the fall of 1845, and then in the spring of 1846, he followed it with a second paper in which he gave his calculated location for the unknown planet. But he got something of the same reaction from French astronomers that Adams had from his English colleagues. So here we are in the middle of the 1840s with two locations known to various astronomers, and incidentally, the two calculated locations were within 1 degree of arc of each other, and yet no one actually looked for the planet. Finally, in the summer of 1846, an English astronomer began actually to search for the planet. But the search didn't go well. There were weather delays, and as before, there was a general lack of enthusiasm. In France, Leverrier was up against the same thing. He became exasperated enough with his astronomer colleagues and their neglect to search the heavens where he told them to look that he finally wrote to a German astronomer in Berlin. He asked a man named Johann Galle to look for the planet. Galle did look in the location Leverrier had specified, and almost immediately found the new planet. That was September 23rd, 1846. And, as you know, the new planet was named Neptune. Now, as I said, the discovery of Neptune illustrates several interesting things about natural science at the time. First of all, it brought a lot of attention to natural science. Everyone was very excited by the discovery of a new member of the solar system. It had happened in their lifetime. And another thing the episode did was to confirm once again the power of science. Here was Leverrier sitting at a table in his workroom, making some calculations based on his extensive knowledge of Newtonian mechanics. And from these scratches on a piece of paper, he had determined the very existence of a new planet. And then he'd told astronomers, who it turned out were hard to get to do their job, he'd said to them, "Look right here, and you'll find the new planet." And that's what happened. The lesson was reinforced that natural science can unearth nature's secrets if one has the ability and the patience to employ the methods of science. But this whole affair also made it clear once again that natural science was not immune to the effect of distinct national rivalries. We've run across them before, in chemistry, for example, and again in the period just prior to the one we're dealing with, in the 1820s, when the British saw themselves as behind the French and Germans. Here in the 1840s, Leverrier's discovery was heralded as an example of the prestige of French science. Of course, the British were not about to sit quietly by and let the French take all the credit. John Herschel observed publicly that Adams had had the solution earlier than Leverrier. But such a blatant attempt to win credit for English science outraged the French. They cried foul. In fact, there's a wonderful cartoon in the Paris journal L'Illustration from 1846 that shows Adams looking through a telescope across the English Channel into a book of Leverrier's. He's depicted as trying to steal Leverrier's calculations while the French astronomer is looking into the heavens. So feelings ran high about the matter. And that just shows how thoroughly natural science was penetrating into the culture. It was part of the emergence of natural science into the public sphere just prior to the middle of the century that I've mentioned now on several occasions. Natural science was clearly being regarded everywhere as of greater and greater importance to society. Now, in our next lecture, we're going to meet another side of astronomy. We'll see that astronomy could outrage people for a very different reason when it investigated the fascinating prospect of whether there was life on other worlds. That will generate its own affair.